Right now, at this very moment, something is happening in our solar system that scientists can't fully explain. And the clock is ticking. We have until early 2026 to get answers. After that, the truth disappears into the void forever. 3I Atlas, the third confirmed interstellar visitor to our solar system. But here's what your telescopes aren't telling you on the evening news. This object is behaving in ways that challenge everything we thought we knew about comets. And some researchers are starting to ask questions that, just a few years ago, would have gotten them laughed out of the room. Let's talk about water. 40 kilograms per second. That's what 3I Atlas is ejecting into space right now. To put that in perspective, imagine a fire hose. Now imagine 80 of them, all running simultaneously, nonstop. That's the scale we're dealing with. But here's the problem. This shouldn't be happening. The distance is 3 astronomical units from the Sun. That's 3 times farther than Earth. At that distance, sunlight is 9 times weaker than what we receive. The temperature is brutal. We're talking minus 180 degrees Celsius in the shade. Water ice shouldn't sublimate at all out there. It should be frozen solid, locked in place, completely inert. Yet, 3I Atlas is gushing water vapor like it's sitting in Earth's orbit. When the Swift Space Telescope detected the hydroxyl signature in October, the signature of shattered water molecules streaming away from the nucleus, scientists had to double-check their instruments. The readings didn't make sense. They still don't. Now, there's an official explanation on the table. Ice grains. Tiny particles of water ice, ejected from the nucleus, carried outward by gas pressure, sublimating as they travel. It's plausible. It fits the physics. But it requires a specific set of conditions that we've never observed in any comet before. The nucleus would need to be extraordinarily active, with gas jets powerful enough to launch macroscopic ice particles into space. And those particles would need to be small enough to sublimate quickly, but large enough to travel far from the nucleus before disappearing. It's possible, but it's also convenient. And convenience in science sometimes means we're missing something. Here's what makes people uncomfortable. The composition. Remember the ratio that stunned everyone? 8 parts carbon dioxide to 1 part water. That's not just unusual. That's extreme. It's a chemical fingerprint that screams, "I'm not from around here." This thing formed in a planetary system with completely different chemistry than ours. A carbon-rich environment, possibly orbiting a cooler star, possibly in the outer regions of a protoplanetary disk that looked nothing like the one that birthed Earth. But there's another detail that doesn't get enough attention. The age. 7 to 10 billion years old. Think about that for a second. This object predates our Sun by 3 billion years. It existed when the universe was less than half its current age, when our galaxy was still young and wild, full of massive stars that lived fast and died young, seeding space with heavy elements. What has this thing seen? Where has it been? And more importantly, what condition would you expect an object to be in after 10 billion years of wandering through interstellar space? Cosmic rays should have shattered the surface. Micrometeoroids should have sandblasted it. The slow grind of deep time should have eroded it into a lifeless, depleted husk. Yet here it is, vigorously outgassing, structurally intact, behaving like a comet that formed yesterday. Unless it didn't spend all that time wandering, unless something protected it, or unless it's not what we think it is. The data from the James Webb Space Telescope added another layer to the mystery. Infrared observations revealed complex organic molecules in the Coma. Not just simple compounds, but chains of carbon and hydrogen that hint at chemical processes we associate with prebiotic chemistry. The building blocks that could, under the right conditions, lead to life. Dr. Dennis Bodwitz from Auburn University put it carefully when he said these ingredients aren't unique to our solar system. But he also noted something else. The molecular patterns don't quite match what we see in our local comets. There are subtle differences in the ratios, in the complexity, in the way the molecules are distributed, as if this thing is showing us a recipe from a different cosmic kitchen. Mars Express managed to image it. Let that sink in for a moment. A spacecraft designed to study Mars, parked in orbit around the red planet, managed to detect an object that was 10,000 to 100,000 times fainter than anything it normally observes. The team had to calculate the trajectory with absurd precision, point the camera at an empty patch of space, and hope the laws of physics held up. And there it was, a faint smudge, barely visible, but undeniably real. Dr. Nick Thomas from the University of Bern called it an amazing technical achievement. But there was something in his tone during the interview, a hint of something else. Excitement, yes, but also puzzlement. Because when you push technology to its limits to observe something that shouldn't even be visible, and you succeed, it raises a question. What else is out there that we're missing? The trajectory is hyperbolic. That's confirmed. It's not gravitationally bound to our sun. It came from somewhere else. And it's going somewhere else. And nothing we do will change that. But here's where it gets interesting. The calculations show it's been traveling for hundreds of millions of years, at minimum, possibly much longer. Through the cold, dark emptiness between stars. No heat, no light. Just the faint whisper of cosmic radiation and the occasional hydrogen atom drifting past. How do you stay active after a journey like that? How do you arrive in a new solar system, still loaded with volatiles, still ready to put on a show? It's like finding a candle that's been burning for 1 billion years. Some scientists think it was in deep freeze the entire time. Temperatures just a few degrees above absolute zero. So cold that even cosmic rays couldn't do much damage. Molecular motion nearly stopped. Everything locked in place, preserved like a biological sample in liquid nitrogen. And then, as it approached our sun, the heat slowly woke it up. That's the conservative explanation. But it requires perfect preservation over cosmic timescales. And nature is rarely that kind. There's another possibility that's been floating around in private conversations, in late-night emails between researchers, in the kind of discussions that don't make it into official papers. What if 3I Atlas isn't as old as we think? What if the 10 billion year age estimate is measuring something else? The age of the material? Yes, but not necessarily the age of the object. What if this thing was ejected from its home system relatively recently? What if there's a planet out there, orbiting a distant star, and something catastrophic happened? A collision, a gravitational perturbation. A rogue planet passing through the system, throwing everything into chaos, and in the aftermath, chunks of ancient ice preserved in the outer reaches of that alien solar system were flung into interstellar space, including this one. That would explain the activity. That would explain the volatiles. And it would mean 3I Atlas is carrying a message. Not an intentional one, but a message nonetheless. A snapshot of a distant planetary system in crisis. A cosmic accident that became our opportunity to study something we could never reach. But here's where we need to be honest. There's a third possibility, and it's the one that makes people nervous. What if it's not a comet at all? The speculation started quietly. A few fringe astronomy forums. Some Reddit threads that mixed genuine curiosity with wild imagination. But then something changed. The conversation started moving into more serious spaces. Academic adjacent blogs. Science journalists asking careful questions. And then, inevitably, the mainstream media picked it up. Could 3I Atlas be an alien spacecraft? Now, before you roll your eyes, let's be clear about something. This isn't ancient aliens territory. This isn't about crystal pyramids or ancient astronauts. This is about legitimate scientists looking at data that doesn't fit the models and asking uncomfortable questions. because that's what science is supposed to do. The comparison to Oumuamua is inevitable. Remember that one? October 2017. The first confirmed interstellar visitor. It wasn't supposed to be controversial. A chunk of rock from another star system passing through, but then it accelerated. Not much. Just a tiny, measurable change in velocity that couldn't be explained by gravity alone. Outgassing, they said. Comets do this all the time. Jets of gas push them off course slightly, except Oumuamua showed no signs of outgassing. No coma, no tail, no dust, no chemical signatures. Just a cigar-shaped object, tumbling through space, accelerating for no visible reason. Professor Avi Loeb from Harvard suggested it might be a light sail, a thin reflective sheet, pushed by sunlight, possibly artificial. The backlash was immediate and fierce. Other scientists proposed alternative explanations: nitrogen ice, hydrogen icebergs, exotic outgassing mechanisms that left no detectable trace, each theory more elaborate than the last. But here's the thing. We never got a good look at Oumuamua. It was gone before we could really study it. So the question remained unanswered. And for some people, it still remains unanswered. 3i Atlas is different. We have time. We have multiple observatories trained on it. We have data. Lots of data. And that data should settle the question definitively. It's a comet. Look at the water vapor. Look at the carbon dioxide. Look at the organic molecules. Case closed. Except the data also raises new questions. The water production at 3AU isn't just unusual, it's physically problematic. The extreme CO2 ratio isn't just different, it's alien in the most literal sense. The preservation over 10 billion years isn't just impressive, it's borderline miraculous. And then there's the shape. We haven't gotten high-resolution images of the nucleus itself. It's too far away, too faint. But based on the light curve, the way brightness changes as it rotates, we can estimate it's somewhere between 2 and 6 kilometers across. That's a huge uncertainty range. It could be round. It could be elongated. It could be irregular like most comets. Or it could be something else. Here's where it gets weird. The rotation appears unusually stable. Most comets tumble chaotically. They're irregular chunks of ice and rock, and as they outgas, jets of material push them into complex spins. But 3i Atlas seems to be rotating smoothly, almost mechanically, as if it's balanced, as if it's designed to spin that way. Is that significant? Maybe, maybe not. But it's noted in the observation logs, filed away. One more data point that doesn't quite fit. There's a pattern here, and the pattern is this. Every time we think we understand 3i Atlas, it does something unexpected. Every time we construct a model that explains the observations, new data comes in that complicates the picture. It's not that any single anomaly is unexplainable. It's that there are so many anomalies. Dr. Matthew Knight from the Naval Research Laboratory was asked directly during a press briefing in late September. Could 3i Atlas be artificial? His answer was diplomatic. He said the simplest explanation is that it's a comet with unusual but natural properties. He said there's no evidence of artificial construction. He said jumping to exotic conclusions is premature. But he didn't say it was impossible. And that matters. The scientific method demands we consider all possibilities and eliminate them systematically. Extraordinary claims require extraordinary evidence. Yes, but extraordinary observations also require extraordinary explanations. And right now, we have extraordinary observations. The water mystery alone is enough to keep researchers up at night. 40 kilograms per second at 3AU requires an energy source. If it's sunlight, the physics barely works, and only if we invoke special circumstances. If it's something else, we need to identify what that something else is. Internal heat? Radioactive decay? That's the natural explanation. Long-lived isotopes, slowly releasing energy, keeping the interior warm. But for an object 10 billion years old, most radioactive elements would have decayed already. You'd need specific isotopes with specific half-lives, in specific concentrations. It's possible. But it's convenient. Chemical reactions? Crystallization of amorphous ice-releasing energy? Again, possible. But again, convenient. And it requires assuming the interior has stayed in a metastable state for billions of years, or something else. Something we haven't considered. Something that doesn't fit our current understanding of comet physics. Here's a thought experiment. Imagine you're an advanced civilization. You want to explore the galaxy. But interstellar travel is hard. Really hard. Even at high speeds, it takes millennia to cross the distances between stars. So what do? You send probes. Automated. Long-lived. Designed to survive millions of years in transit. And you disguise them. Because if there's one thing that moves freely through space, unnoticed and unremarkable, it's a comet. You build your probe to look like a comet. You coat it in ice. You program it to outgas at appropriate times. You give it a composition that will blend in with natural objects. And you send it on a trajectory that will take it through promising star systems. Slowly, over eons, gathering data. Is that what 3I Atlas is? Almost certainly not. The odds are astronomically against it. The evidence suggests it's exactly what it appears to be. A natural object. A chunk of ancient ice from an alien world. Fascinating, yes. Historic, absolutely. But natural. But can we be absolutely 100% certain? Not yet. Not until we've exhausted every natural explanation. Not until we've explained the water at 3AU, the extreme composition, the stable rotation, the preserved volatiles. Not until all the puzzle pieces fit perfectly. And here's the deadline. Early 2026. By then, 3I Atlas will have passed perihelion, the closest point to the sun, and begun its journey outward. It will fade. Observations will become difficult, then impossible. We'll have all the data we're going to get, and whatever conclusions we draw, we'll have to live with them. Because this isn't Oumuamua. This time, we got a good look. This time, we did the science right. This time, we collected the data. And when it's gone, when it's just another fading point of light disappearing into the cosmic dark, we'll know the truth. Or at least, we'll know what the data tells us. Whether that's the same thing as the truth, well, that's a different question entirely. The unusual stability, the impossible water production, the ancient yet active nature, the chemical fingerprint of an alien world. These are facts. What they mean, that's interpretation. And interpretation depends on assumptions. Assumptions about what's possible, what's probable, what's worth considering. Some researchers are starting to suggest additional observations. Not just passive watching, but active probing. Radio telescopes scanning for any electromagnetic emissions. Radar imaging to get a better look at the nucleus structure. Spectroscopy pushed to the limits, searching for anomalies in the chemical signatures. Anything that might resolve the ambiguities. Because ambiguity is what breeds speculation. And right now, 3I Atlas is swimming in ambiguity, drowning in it. Every new observation clarifies some details while muddying others. Every answer raises two new questions. That's the nature of frontier science. That's what it feels like when you're studying something truly novel. Confusion and clarity, dancing together. And somewhere in that dance, the truth is waiting to be discovered. But what if the truth is stranger than we're prepared for? What if the natural explanation, however complex, however unlikely, is still less strange than the alternative? What then? We'll find out soon enough. The clock is ticking, And 3I Atlas isn't slowing down. Let's talk about what 3I Atlas is made of, because this is where the story gets really interesting and really strange. 8 to 1. That's the ratio. 8 parts carbon dioxide for every 1 part water. When scientists first calculated this from the spectroscopic data, there was a moment of stunned silence in several observatories around the world. Not because high CO2 ratios are impossible. We've seen carbon dioxide-dominated comets before, but never like this. Never this extreme. Most comets in our solar system have the opposite profile. Water dominates. Carbon dioxide is the minority component. That makes sense because water ice is abundant in the regions where comets form. The outer solar system, the Kuiper belt, the Oort cloud, these are water-rich environments. Carbon dioxide exists, sure, but it's a supporting player, not the main character. 3I Atlas flips that script entirely. This is a comet where carbon dioxide is the primary volatile, and water is the afterthought. That tells us something profound about where it formed. We're looking at chemistry from a planetary system with fundamentally different conditions than ours. A cooler star, perhaps? Spectral class K or M. Red dwarfs or orange dwarfs, smaller and dimmer than our sun. In systems like that, the frost line, the distance where water freezes, sits much closer to the star. The outer regions where comets form would be extremely cold and carbon-rich. Carbon monoxide, carbon dioxide, methane, these become the dominant ices, or a different stage of stellar evolution. Maybe 3I Atlas formed in a system where the parent star was still very young, and the protoplanetary disk was rich in carbon from recent supernovae nearby. The early universe had different chemical patterns, more carbon relative to oxygen in some regions, different elemental abundances that shaped what could form. The point is, this chemistry is alien, literally. It's telling us that planetary systems can be wildly different from ours, and that has implications for everything. For planet formation theory, for the diversity of worlds, for the possibility of life elsewhere. But here's the paradox. If 3I Atlas is so carbon-rich, why is it producing so much water? 40 kilograms per second of water vapor. That's not trace amounts. That's substantial outgassing. For a comet with an 8 to 1 CO2 to water ratio, that level of water production implies the carbon dioxide outgassing must be absolutely enormous. We're talking hundreds of kilograms per second. Maybe more, and we should be seeing that. Carbon dioxide has strong infrared signatures. JWST is specifically designed to detect infrared radiation. When they pointed JWST at 3I Atlas, they should have seen a blazing signature of CO2 outgassing, a clear, unmistakable signal. They saw it, but it wasn't as strong as expected. The ratio in the Coma, the cloud of gas surrounding the nucleus, didn't quite match the ratio calculated from the overall composition, as if the water is being preferentially released somehow, as if something is separating the volatiles. Now, there are natural explanations. Layering, for instance. Maybe the nucleus has a water-rich outer layer and a CO2-rich interior. As the surface erodes, we see more water early on, and the composition will shift as we dig deeper into the object. That happens with comets. Their surfaces are heterogeneous, patchy, complex, but the observations don't quite support that either. The outgassing appears uniform across the visible nucleus. No strong jets from specific locations. No obvious active regions. Just a general, distributed release of material, as if the entire surface is participating equally. Another possibility is subsurface activity. Maybe the water is coming from below, percolating through cracks and fissures, while the CO2 sublimates directly from the surface. Different volatiles, different pathways to escape. That could create the observed discrepancy. Possible. But it requires a specific internal structure, porous enough for gas to migrate, but strong enough to maintain structural integrity. And remember, this object is 10 billion years old. How does porosity survive that long? How do pathways remain open? Unless they were designed to remain open. Unless the structure isn't random. Stop. Let's not go there yet. Let's stay with the natural explanations. The JWST data revealed something else. Complex organic molecules. Not just simple stuff like methane or formaldehyde. We're talking about larger structures, polycyclic aromatic hydrocarbons, long carbon chains with attached hydrogen, precursors to the kind of chemistry that, in the right environment, could lead to amino acids, to nucleotides, to the building blocks of life. This is huge. This is exactly what astrobiologists have been hoping to find. Evidence that the ingredients for life aren't unique to Earth, aren't even unique to our solar system. They're out there, everywhere, distributed by comets and asteroids and interstellar visitors. The galaxy is seeding itself with the potential for biology. But the distribution pattern is odd. The organic molecules aren't evenly mixed with the water and CO2. There are concentration gradients. Certain molecules appear more abundant in certain regions of the coma, as if they're being released from specific areas, or at specific times, or under specific conditions. Natural? Almost certainly. Comets are heterogeneous. Their surfaces vary. Their compositions vary. Finding variations in the outgassing products is expected. But the pattern is curious. Some researchers have noted that the organic molecule distribution seems almost, and this is a very careful word choice, strategic. As if material is being released in a controlled manner. Not random, not chaotic. Controlled. That's reading too much into noisy data. That's seeing patterns where none exist. That's exactly the kind of overinterpretation that leads to bad science. But what if it's not overinterpretation? What if the pattern is real? Here's another data point. The dust. Comets release dust along with gas. Tiny particles, blown off the surface, reflecting sunlight, creating the visible tail. 3I Atlas has dust. Spectroscopic analysis shows silicates. Expected. Carbonaceous material. Expected. Some metal oxides. Typical. But the particle size distribution is unusual. Most comets have a power law distribution. Lots of tiny particles. Fewer medium particles. Very few large particles. That's what you get from random fragmentation processes. Natural erosion produces that pattern. 3I Atlas has too many medium-sized particles. The distribution is flatter than expected. As if something is generating particles in a specific size range preferentially. As if there's a process selecting for particles around 10 to 50 micrometers. Why would nature do that? Well, maybe it's the way the surface material fractures. Maybe the composition creates a specific fragmentation pattern. Maybe thermal stress produces particles in that size range. Or maybe, and this is speculation, pure speculation, but maybe particles in that size range are optimal for certain purposes. Radar reflection, for instance. Or light scattering. Or thermal regulation. No, that's going too far. That's conspiracy thinking. That's seeing intent where there's only physics. But the data is there. Filed in observation logs, waiting for explanation. The spectroscopic signatures have another oddity. There are absorption features that don't quite match known compounds. Tiny dips in the spectrum at specific wavelengths. Could be instrumental artifacts. Could be noise. Could be overlapping signals from multiple molecules creating a blended signature that looks anomalous. Or could be something we haven't seen before. A molecule that doesn't exist in our solar system. A compound that forms under conditions we've never replicated. Chemistry from an alien world. That would be the scientific discovery of the century. Confirmation that organic chemistry in other star systems can produce novel compounds. that the universe is more chemically diverse than we imagined. That our laboratories, for all their sophistication, represent only a tiny fraction of what's possible. But confirming that requires eliminating every other possibility. And that takes time. Time we're running out of. The coma itself has structure. Not just a uniform cloud, but filaments, streamers, regions of higher and lower density. That's normal for comets. Solar wind and radiation pressure shape the coma, create structures, produce patterns. But the structures around 3I Atlas seem persistent. They don't change the way you'd expect from purely external forces, as if there's an internal component to the shaping, as if the nucleus is releasing material in specific directions, maintaining certain patterns. Could be rotational effects. As the nucleus spins, active regions face the sun at different times, creating a rhythmic pattern of outgassing that manifests as structure in the coma. But the rotation period, estimated from brightness variations, is about 12 hours. The coma structures persist for days, weeks even. They should smear out, dissipate, reform in different configurations. They don't. They hold their shape longer than models predict. Why? What's stabilizing them? What's maintaining the structure? There's a paper being prepared right now, expected to be published in early 2026, that will attempt to model the coma dynamics with unprecedented detail. High-resolution simulations, incorporating solar wind, radiation pressure, magnetic fields, everything they can think of. The goal is to reproduce the observed structure using only natural forces. If they succeed, case closed. It's a comet. Complex, yes. Unusual, absolutely. But natural. If they fail, if the models can't reproduce the observations, then we have a problem. Then we need new physics, or new assumptions, or a completely different interpretation of what we're looking at. The composition of 3I Atlas isn't just data. It's a puzzle. A multi-layered, interlocking puzzle where every piece connects to every other piece, and nothing quite fits together the way it should. That's exciting. That's what frontier science looks like. But it's also unsettling, because when you can't make the pieces fit, you start to wonder if maybe you're looking at the puzzle wrong. If maybe the picture you're trying to assemble isn't the picture that's actually there. There's a date circulating in astronomical circles. Not an official deadline, not a formal announcement, but a consensus among researchers who are tracking 3I Atlas. Early 2026. Sometime between January and March. That's when we'll know. By then, 3I Atlas will have reached perihelion, the closest approach to the Sun. That moment will occur in late December 2025. It will be at approximately 1.8 astronomical units. Closer than Mars. Still far, but close enough that solar heating will reach its maximum. If there's anything unusual about this object, anything that will only reveal itself under peak thermal stress, that's when we'll see it. And then it begins its outward journey. Fading. Cooling. The outgassing will decline. The brightness will drop. Within weeks, it will become difficult to observe. Within months, impossible for most telescopes. By mid-2026, it will effectively be gone, swallowed by distance and darkness. So the window is closing. The observations are intensifying. Every major observatory that can point in its direction is doing so. Data is accumulating at an unprecedented rate. Terabytes of information, spectroscopic scans, imaging sequences, photometric monitoring, radar attempts. And somewhere in all that data, the answer is waiting. The question is, what will that answer be? Scenario 1. The natural explanation holds. Every anomaly finds a conventional explanation. The water at 3AU is from ice grain ejection, confirmed by refined modeling. The composition reflects a carbon-rich formation environment, consistent with certain types of planetary systems. The age is genuine, and the preservation is due to the deep freeze of interstellar space. The stable rotation is just a coincidence, or a result of outgassing patterns we finally understand. The organic molecules are distributed unevenly because comet surfaces are heterogeneous. The dust particle size distribution is a result of specific fragmentation physics. The persistent Coma structures are reproduced in updated simulations. Everything fits. It's a comet. Remarkable, historic, scientifically invaluable. But natural. A 10 billion year old chunk of ice from an alien star system, giving us a glimpse into planetary formation processes we could never observe directly. That alone would be worth celebrating. That alone would rewrite textbooks. And honestly, that's probably what will happen. That's what the data most likely shows. A comet. Just a really, really weird comet. Scenario 2. The natural explanation doesn't quite hold. Some anomalies persist. The models can't fully account for the observations. New data from perihelion reveals additional unexpected behaviors. Maybe the outgassing increases in ways that don't match predictions. Maybe the rotation changes, indicating internal mass redistribution that doesn't make sense for a solid ice ball. Maybe the spectroscopic signatures shift, suggesting chemical processes that shouldn't be occurring. In that case, we don't have an answer. We have a mystery. And the scientific community will debate it for years. Papers will be published arguing different interpretations. Models will be refined. New theories will be proposed. And 3i Atlas will become one of those objects that divides opinion, where some researchers are convinced it's just a poorly understood natural phenomenon, and others quietly wonder if there's something more. That would be frustrating. That would leave us hanging. But it would also be honest. Science doesn't always give clean answers. Sometimes the data is ambiguous. Sometimes we have to live with uncertainty. Scenario 3. Something happens that can't be explained naturally. And this is the scenario that makes people nervous. What would that look like? An unambiguous signal. An acceleration that can't be attributed to outgassing. A radio emission at a frequency that screams artificial. A geometric pattern in the coma that's too regular to be coincidence. A change in trajectory that violates conservation of momentum unless there's an internal propulsion system. Something that forces us to consider the possibility we've been avoiding. That 3i Atlas isn't natural. That it's technology. That we're not looking at a comet from another star system. We're looking at a probe. The reaction would be immediate and massive. Every telescope on Earth and in space would focus on it. Emergency observing time would be allocated. Governments would get involved. The media would explode. And the scientific community would fracture into camps. Those demanding extraordinary evidence. Those arguing the data already constitutes extraordinary evidence. Those trying to find alternative explanations. Those accepting the implications. It would change everything. Not just astronomy. Everything. The knowledge that we're not alone. That another intelligence exists. Or existed. That they built something, sent it out into the galaxy, and it made its way here. But here's the thing. We're not going to get a clear signal. We're not going to detect a radio transmission. We're not going to see geometric patterns. Because if 3i Atlas were artificial, if it were a probe from another civilization, it wouldn't advertise itself. Why would it? If you're sending a probe to explore, you design it to blend in, to look natural, to observe without being observed. So even if scenario 3 is true, we might never prove it. We might only have the anomalies, the unexplained data points, the pattern of strangeness that could be natural, but could also be something else, and we'd be left guessing. That's the frustrating reality. The universe doesn't owe us clear answers. But there's another consideration. Perihelion isn't just when 3i Atlas is closest to the Sun. It's also when it's closest to Earth. The geometry works out such that in late December, we'll have the best viewing angle we're ever going to get. the distance will be relatively small. The light will be strong. If there's anything to see, any detail that's been hidden by distance and faintness, that's when we'll see it. Hubble is scheduled for extended observations during that window. The images won't be close-ups. We're not going to see surface features in detail, but we'll see the nucleus more clearly than before. We'll be able to refine the size estimate. We'll see if the shape is unusual. We'll look for asymmetries, irregularities, anything that stands out. JWST will conduct its most detailed spectroscopic analysis during perihelion. Every wavelength it can observe, every molecular signature it can detect, all focused on this one object for a concentrated period. If there are exotic compounds, if there are chemical processes that only activate under higher solar flux, this is when we'll catch them. Ground-based observatories in Chile, Hawaii, and the Canary Islands are coordinating a multi-night campaign. Continuous monitoring, photometry, spectroscopy, polarimetry, radar if possible, though the distance is at the edge of radar range. They want a complete picture, a dataset so comprehensive that future researchers will be able to reanalyze it for decades. And the Mars orbiters are going to try again. Mars Express and the Trace Gas Orbiter will attempt additional imaging when the geometry is favorable. Last time, they barely caught it. This time, with better planning and refined calculations, they hope to get clearer images. Maybe even resolve the nucleus as more than just a single pixel. Maybe see something about its structure. It's a coordinated global effort, the kind of thing that only happens for truly significant events. And the fact that it's happening tells you something. The scientific community is taking this seriously. They know this is important. They know we might not get another chance. Because after perihelion, after 3I Atlas swings around the sun and heads back out into the dark, it's gone. Its trajectory will carry it away from our solar system, back into interstellar space, off toward whatever lies in that direction. And given its speed, given the vast emptiness between stars, it will be hundreds of thousands of years before it approaches another star system. Maybe millions. This is our only chance. This moment. This brief window when an object from another world passes through ours, and we have the technology to study it, and we have the will to do so. Miss it, and we miss it forever. So the pressure is on. The observations are ramping up. The data is flowing. And in a few months, when the analysis is complete, when the papers are written, when the press conferences are held, we'll hear the verdict. Comet. Definitely a comet. Unusual, yes. Unprecedented in some ways. But natural. Case closed. Or comet, probably. Most likely natural. Some anomalies remain unexplained, but that's normal in science. We need more data, which we won't get. The mystery persists. Or we don't know. The data doesn't fit the models. Something is going on that we don't understand. It might be natural, it might not. We can't say for certain. And now it's too late to investigate further. 3 outcomes, 3 possibilities, and we're about to find out which one is real. Unless there's a 4th outcome. One nobody is talking about publicly. One that lives in whispered conversations and speculative late-night thoughts. What if 3I Atlas knows we're watching? What if it's been dormant, coasting, pretending to be a comet, and perihelion is when it does whatever it came here to do? What if the timing isn't coincidence? What if we're about to witness something that will change everything we think we know about our place in the universe? That's science fiction thinking. That's letting imagination run wild. That's not how we should approach this. But what if? Let's step back for a moment. Let's look at the bigger picture. Because 3I Atlas isn't happening in isolation. It's part of a pattern, and patterns tell stories. 2017, Oumuamua. The first confirmed interstellar object. Cigar-shaped, tumbling, accelerating without visible cause. It defied easy categorization. Was it a comet? An asteroid? Something else? We never got a definitive answer because it was gone before we could really study it. But it opened our eyes to a reality we'd suspected but never confirmed. Objects from other star systems pass through ours regularly. 2019, Borisov, the second interstellar visitor. This one was reassuring. It looked like a comet. It acted like a comet. Spectroscopy showed water, carbon monoxide, the usual suspects. Its composition was different from our local comets, yes, but understandably different. It came from another system, after all. Borisov told us that not all interstellar visitors are weird. Some are exactly what we expect. 2025, Three-Eye Atlas, the third visitor. And suddenly we're back to weird, extreme composition. Impossible water production. Ancient beyond measure. Active beyond reason. All the questions Oumuamua raised, but with better data. All the ambiguity, but with more time to study. 3 objects. 3 completely different profiles. What does that tell us? It tells us the galaxy is diverse. Wildly, incredibly diverse. Every planetary system has its own story, its own formation history, its own chemical environment, its own processes for creating and ejecting material. And those differences are profound. But there's something else. A statistical reality that most people don't think about. We've detected 3 interstellar visitors in 8 years. 3. That sounds rare. That sounds like a once-in-a-blue-moon occurrence. But here's the thing. We only detect the ones that come close. The ones that pass within a few astronomical units of the sun, where they're bright enough to spot, where their trajectories are obviously hyperbolic, where we have a chance of noticing them. The vast majority pass through undetected, too far away, too faint, moving through the outer solar system where our surveys don't reach. Astronomers estimate that at any given time, there are probably several interstellar objects within the orbit of Neptune. We just don't see them. And if we extend that out, if we consider objects passing through the wider solar system, the numbers become staggering. Potentially thousands per year. Maybe tens of thousands. The galaxy is full of this stuff. Ejecta from planetary systems. Debris from stellar encounters. Fragments of worlds that never formed, or formed and were destroyed. All of it drifting through space, occasionally crossing paths with stars like ours. We live in a cosmic shooting gallery, and we're only just starting to realize it. That context matters when we think about Three-Eye Atlas, because if interstellar visitors are common, if there are thousands of them passing through unnoticed, then the odds of any one of them being artificial drop considerably. You'd need a galaxy teeming with spacefaring civilizations, all sending out probes for artificial objects to represent a significant fraction of the total. And we have no evidence of that. No radio signals, no megastructures, no obvious signs of galactic engineering. The Fermi paradox stands. Where is everybody? If intelligent life is common, where are the artifacts? Where are the traces? Maybe they're hiding. Maybe they're extinct. Maybe we're looking in the wrong ways. Or maybe they're rare. Maybe intelligence is a fluke. Maybe we're among the first. Or the only. But if that's true, if artificial interstellar probes are rare or non-existent, then Three-Eye Atlas is almost certainly natural. Just another chunk of ice, however weird it might be. Almost certainly. That word matters. Almost. Because there's another statistical consideration. If you're an advanced civilization wanting to explore, you don't send probes to random star systems. You target interesting ones. Systems with planets. Systems with potential for life. Systems worth investigating. Our solar system is interesting. 8 planets. A habitable zone containing a world with liquid water and a biosphere. Complex chemistry. Active geology. It's exactly the kind of system you'd want to study if you were looking for life. And we're not hidden. Our sun has been here for 4.5 billion years. Life has been on Earth for most of that time. Oxygen has been in our atmosphere for over 2 billion years. Any civilization with decent telescopes could detect the oxygen signature from hundreds of light years away. They'd know this is a biosphere. They'd know it's worth investigating. So if probes exist, if anyone has sent automated explorers into the galaxy, our solar system would be on the target list. Not necessarily at the top, but somewhere on the list. That doesn't mean 3i Atlas is a probe. It just means the possibility isn't as absurd as it might seem at first glance. Context matters. Statistics matter. And there's one more piece of context that matters: our own plans. We're designing interstellar missions. Right now. Today. Breakthrough Starshot is developing concepts for tiny probes accelerated by laser arrays, reaching a fraction of light speed, traveling to nearby stars within a human lifetime. NASA has studied concepts for larger, slower missions. Nuclear pulse propulsion, fusion drives, generation ships. We're thinking about sending something to Alpha Centauri, to Proxima Centauri, to whatever targets look interesting. And when we design those missions, we think about longevity. We think about autonomy. We think about building something that can survive the journey, complete the mission, and return data across light years of distance. If we're thinking about it, others might have done it. Others might be doing it right now. Others might have done it 1 billion years ago, and their probes are still out there, still functional, still exploring. That's not speculation. That's extrapolation. If we can imagine it, if we're working toward it, it's not unreasonable to assume others might achieve it. But there's a gap between might exist somewhere and is here right now. A vast gap. And jumping across that gap requires evidence. Solid, unambiguous evidence. Do we have that for 3i Atlas? No. We have anomalies. We have unexplained data. We have puzzles. But we don't have proof. We don't have a smoking gun. And maybe we never will. Maybe the nature of the situation is such that proof is impossible. If a probe is designed to look natural, how would you prove it's not? You can't. You can only pile up coincidences and anomalies until the weight of them becomes uncomfortable, until the natural explanations start to feel forced, until you're left with a choice between accepting a highly unlikely natural scenario or considering an even more unlikely artificial one. That's where 3i Atlas might leave us, in that uncomfortable space, where both explanations seem wrong, but one of them has to be right. The scientific community will default to natural. That's the correct approach. Extraordinary claims require extraordinary evidence. Absent that evidence, the null hypothesis stands. It's a comet. End of story. But some researchers will keep wondering. They'll keep the data. They'll keep analyzing. And if future observations reveal something new, something that changes the picture, they'll be ready. Because here's the final piece of context. We're getting better at this. Every year, our telescopes improve. Our survey capabilities expand. Our ability to detect and characterize interstellar visitors increases. The Vera Rubin Observatory comes fully online soon, and it will revolutionize sky surveys. It will catch objects we're currently missing. It will find interstellar visitors earlier, giving us more time to study them. The next Oumuamua won't escape us. The next 3i Atlas will be observed from the moment it enters the solar system until it leaves. We'll have complete data, complete coverage, complete understanding. And if any of those future visitors show unambiguous signs of being artificial, we'll know. There will be no room for doubt. But for now, for 3i Atlas, we're working with what we have. Incomplete data, limited observation windows, ambiguity, and a growing sense that we're witnessing something important, something that will be remembered. Whether it's the most unusual comet ever observed or something more, This is a moment, a turning point. The era when humanity stopped being surprised by visitors from other stars and started studying them routinely. We're transitioning from discovery to understanding, from shock to analysis, from what is that to what does it tell us. That's progress. That's growth. That's us becoming a civilization capable of thinking on galactic scales. 3i Atlas is part of that story. A strange, perplexing, fascinating part. And whatever it turns out to be, it's teaching us about comets, about planetary systems, about diversity, about the universe, and maybe, just maybe, about ourselves, about our place in the cosmos, about what it means to look up at the sky and realize we're not looking at a distant, empty void. We're looking at a neighborhood, a busy, populated, dynamic neighborhood where things move and interact and occasionally cross paths. We're not alone in the sense of being isolated. We're part of a galactic ecosystem. Matter flows between stars. Objects travel between systems. Chemistry mixes. The universe is connected in ways we're only beginning to appreciate. 3i Atlas is one thread in that vast web. One visitor in an endless stream. One messenger from the deep past, carrying information across space and time. And for a brief moment, it's ours to study. Ours to wonder about. Ours to try to understand. The clock is still ticking. Perihelion approaches. The answers are coming. So, where does that leave us? Right here. October 2025. 3i Atlas is getting brighter as it approaches the sun. The observation campaigns are ramping up. Data is flooding in faster than researchers can analyze it. And we're all waiting for perihelion. Late December. That's the moment of truth, when 3i Atlas comes closest to the sun, when solar heating reaches maximum intensity, when whatever volatiles are buried in that ancient nucleus will respond with maximum vigor. If there's anything this object has been hiding, anything that only reveals itself under peak illumination, that's when we'll see it. Every prediction model, every simulation, every theoretical framework is pointing toward that date. Researchers have their hypotheses ready. Natural explanations lined up. Alternative scenarios prepared. They know what they're looking for. They know what data to collect. They know what measurements will be decisive. But there's always the possibility of surprise. Always the chance that nature, or something else, has one more trick to show us. The imaging campaign will be intense. Hubble will be watching continuously during the critical period. Its sharp optical resolution will capture the nucleus in the best detail we're capable of from this distance. Any asymmetry, any unexpected feature, any deviation from the expected shape, it will be recorded, archived, available for analysis and reanalysis for decades to come. JWST will be running its full spectroscopic suite, infrared wavelengths from near to mid-range, every molecular signature visible in that part of the spectrum. The goal is a complete chemical inventory, not just water and CO2, but everything else. Methane, ammonia, carbon monoxide, complex organics, anything that's outgassing. And more importantly, the ratios, the relative abundances, the patterns that reveal formation conditions. If the models are right, the spectroscopic data will show increased water and CO2 production as solar flux intensifies. The ratio should stay relatively constant or shift in predictable ways based on their different sublimation curves. The organic molecules should increase proportionally. Everything should scale up together. If the models are wrong, we'll see deviations. Unexpected molecules appearing. Ratios changing in ways that don't match simple heating. Signatures that suggest chemistry more complex than passive ice sublimation. And if there's something truly anomalous, truly unexplainable, the data will capture it. There's no hiding at perihelion. The sun illuminates everything. Ground-based observatories will provide continuous monitoring. What space telescopes lack in time coverage, Earth-based systems can provide. Multiple facilities distributed across longitudes, ensuring round-the-clock observation. If something transient happens, if there's a sudden burst of activity or an unexpected change, it will be caught. The Mars orbiters will make their second attempt. Better timing this time, better positioning. The images won't be spectacular. We're not going to see surface features or fine details, but we might resolve the nucleus shape more clearly. We might see if it's elongated, spherical, irregular. That alone would be valuable. And radar. There's a possibility of radar observation from Arecibo. Wait, no. Arecibo collapsed in 2020. That's gone, but other facilities exist. Goldstone in California, the Green Bank Telescope. They're not as powerful as Arecibo was, but they might have a chance. Radar can penetrate the Coma, see through the gas and dust, get a direct measurement of the nucleus, size, rotation, maybe even crude shape information. If radar succeeds, it would be huge. It would give us ground truth data, literally. No more estimating from brightness and assumptions. We'd know the size. We'd know the spin rate precisely. We'd know if there are large-scale structures on the surface. But radar is difficult. The object is far. It's relatively small. The signal return will be weak. It might not work. But they're going to try. All of this. All these observations. All this data. It's building toward a comprehensive picture. The most complete characterization of an interstellar visitor ever achieved. Oumuamua escaped before we could really study it. Borisov was better documented, but it was rushed. We had to scramble to observe it before it faded. 3i Atlas is different. We've had time. We've had preparation. We've coordinated. This is what it looks like when the global astronomical community works together toward a common goal. This is humanity at its best. Curious, methodical, determined to understand. And after perihelion, after the observation window closes, the real work begins. Data analysis, modeling, paper writing, conferences, debates. The observations take weeks. The understanding takes years. Papers will be published throughout 2026 and beyond, each focusing on different aspects: composition, activity, trajectory, organic molecules, dust properties, Coma dynamics. Every research group will contribute their piece of the puzzle, and eventually a consensus will emerge. Maybe not immediately, maybe not cleanly, but over time, the scientific community will settle on an interpretation. This is what 3i Atlas is. This is where it came from. This is why it behaves the way it does. That interpretation will likely be natural. A comet. Unusual, yes. Extreme in some properties, but ultimately explainable within known physics and chemistry. The anomalies will be resolved, or at least understood well enough to be comfortable with. But there's a possibility, however small, that the consensus will be different, that the data won't fit, that the anomalies won't resolve, that we'll be left with something unexplainable. And if that happens, if we reach the end of this investigation, and we still don't understand what 3i Atlas is, then the conversation changes. Then we have to seriously consider alternatives, not as wild speculation, but as legitimate scientific hypotheses worth investigating. That would be uncomfortable. That would challenge us, but it would also be exciting. It would mean the universe is stranger than we thought, that there are phenomena we haven't accounted for, that our understanding is incomplete. Science thrives on incomplete understanding. That's what drives progress. The questions we can't answer today become the breakthroughs of tomorrow. So whatever 3i Atlas turns out to be, we win. If it's natural, we learn about comet diversity and planetary system formation. If it's something else, we learn about the limits of our current knowledge and where to push next. Either way, we're better off for having encountered it, for having observed it, for having tried to understand it. And here's something to think about. Right now, there are probably dozens of other interstellar visitors passing through our solar system. We just don't see them. They're too far out, too faint, too small. But they're there, carrying their own stories, their own chemistry, their own secrets. In a few years, when the Vera Rubin Observatory is in full operation, we'll start catching them. Not just the bright ones that pass close, but the faint ones, the distant ones, the small ones. We'll be finding interstellar objects regularly, monthly maybe, weekly, eventually, and each one will teach us something. Each one will be a sample from a different star system, a different planetary formation environment, a different cosmic history. We're entering an era where interstellar visitors stop being extraordinary and start being routine, where we build up a catalog, a database, a statistical sample large enough to draw meaningful conclusions about the galaxy as a whole. 3I Atlas is part of that transition. It's one of the first, one of the pioneers, and it's teaching us not just about itself, but about how to study objects like it, what observations to make, what data to collect, what questions to ask. Future astronomers will look back at this moment and see the beginning of interstellar comparative planetology. The point where we stopped being limited to our own solar system and started sampling the galaxy directly. That's profound. That's historic. That's worth appreciating even before we know all the answers. So as we watch 3I Atlas approach perihelion, as we wait for the data, as we prepare for whatever revelations December brings, remember this. You're witnessing something rare, not just the object itself, but the moment. The moment when humanity looked up, saw a visitor from another star, and had the tools and knowledge to study it properly. Our ancestors saw comets and feared them, thought they were omens, portents of disaster. We see comets and we measure them. We analyze their chemistry. We calculate their orbits. We extract information. That transformation from fear to understanding is what civilization is all about. And 3I Atlas is the latest chapter in that ongoing story. It's out there right now, moving through space at 210,000 kilometers per hour. Ancient, mysterious, carrying the signature of a star system we'll never visit. And for a brief, precious window of time, it's close enough for us to see. In a few months, it will be gone, fading back into the darkness, continuing its journey through the galaxy, and we'll be left with our data, our observations, our interpretations, and the knowledge that we did our best. We looked, we measured, we tried to understand, and maybe, just maybe, we'll have learned something about what's out there, about what's possible, about what the universe has been doing for billions of years while we weren't watching. The next interstellar visitor is already on its way. Somewhere out in the dark, another ancient traveler is approaching, another object with another story, and when it arrives, we'll be ready. We'll be watching. We'll be learning. Because that's what we do now. We study the galaxy one visitor at a time. We piece together the cosmic puzzle. We expand our understanding one strange, wonderful, perplexing object at a time. 3I Atlas is one piece of that puzzle, a big piece, an important piece. And whatever it reveals, it's bringing us closer to understanding the universe we live in. The clock is ticking. Perihelion is coming. The moment of truth approaches. And somewhere, deep in the void, 3I Atlas continues its ancient journey, unaware or uncaring that for this brief moment it has our complete attention, that telescopes across Earth and in space are focused on it, that thousands of scientists are analyzing its every photon, that humanity is watching, wondering, and waiting for answers. Whatever those answers turn out to be, the journey to find them has been worth it. That's the real discovery. Not what 3i Atlas is, but what we've become. A species capable of studying visitors from other stars. A civilization reaching beyond our cosmic neighborhood. Minds that can look at something 10 billion years old and ask not just, what is it? But, what can it teach us? Early 2026. That's when we'll know. Mark your calendars. Watch the news. Follow the scientific papers. Because whatever happens, it's going to be significant. One way or another, 3i Atlas is going to tell us something we didn't know before. About comets. About planetary systems. About the galaxy. About the universe. Or maybe, just maybe about ourselves. The truth is coming, and we're ready for it. Whatever it is.